Hello everyone, in this video I'll walk you through three different implementations of neural networks for solving regression problems. First, let's look at our NumPy implementation. Here I created a neural network from scratch using only NumPy. We begin by generating synthetic data for a nonlinear regression problem. Our input features are three variables, x1, x2 and x3, and our target output is the sum of their squares. So visualizing this data in 3D to understand what we are working with, each point color represents its target value. Now for the neural network architecture, we're implementing a simple feed-forward network with an input layer with 3 neurons for our three features. A hidden layer with 5 neurons using ReLU activation, and input layer with a single neuron using linear activation. We then initialize our weights and biases randomly and define our activation functions, ReLU for the hidden layer and linear for the output. The forward propagation function passes our input through the network, calculating the predicted output values. For training, we use mean squared error as our loss function and implement backward propagation to update our weights and biases using a gradient descent. And then we visualize our results. This loss curve shows how our model improves over time, and this scatter plot compares true values versus predicted values. The closer to a diagonal line, the better our predictions are. And now moving on to the next collab, we'll implement a neural network in PyTorch but still build it from scratch without using built-in layer models. So in this collab, we are generating different synthetic data, a simple quadratic function with some noises added. Our input is one-dimensional, making it easier to visualize. We define a neural network class that inherits from Torch, but we manually create and manage the weights and biases as parameters. Here our architecture has an input layer with one neuron, two hidden layers with 5 neurons each using ReLU activation, and output layer with one neuron. And then we implement matrix multiplication and activation functions manually, similar to our NumPy implementation, but utilizing PyTorch tensor and automatic differentiation. The plot shows our training loss decreasing over time and predictions, which is the red lines, closely matching the true data in blue points. And now moving on to the next collab, we see how simpler our code becomes when using PyTorch built-in models. We use the same synthetic quadratic data as we used before. This time our neural network class uses torch.linear models to define each layer, which automatically handle weights and biases for us. The forward method becomes much cleaner with activation applied directly to the outputs of each layer. For optimization, we can now use PyTorch built-in optimizers like SGD instead of manually updating parameters. Our training loop is similar but simpler. We zero gradients, compute the forward pass, calculate the loss, perform back propagation, and update parameters using the optimizer. The results are comparable to our previous implementation, but the code is significantly cleaner and easier. And now moving on to the next collab. This is for the PyTorch Lightning, which builds on PyTorch to simplify the training process. We install the PyTorch Lightning and import the necessary libraries. We'll then use the same synthetic quadratic data as our previous examples. PyTorch Lightning organizes code into a specific structure. Here we create a Lightning NN class that inherits from Lightning model. This class combines the model architecture, training process, and data handling. For the model architecture, we define three layers. Just like in PyTorch example, the forward method remains the same with ReLU activations between layers. What's different is that we add specific methods that Lightning requires. Configure optimizers, where we define our SGD optimizer, training step, where we compute and return the loss for each batch, train data loader, where we define how to load our training data. To train the model, we simply create a Lightning trainer object specifying the number of epochs and other training configurations, then call trainer.fit with our model. After training, we can visualize our results just like before. The plot shows our predictions closely matching the true quadratic function. PyTorch Lightning provides this clean organization while handling many training details behind the scenes, like tracking metrics and managing the training loop. And on the next collab, we'll implement a neural network from scratch using TensorFlow low-level API. We generate the same synthetic quadratic data and convert it to TensorFlow tensors. Similar to our NumPy implementation, we manually define the weights and biases and as TensorFlow variables, which can be updated during training. Our forward function implements the model architecture with three layers and ReLU activations between them. For back for backpropagation, TensorFlow provides automatic differentiation through gradient tape. In our backward function, we record our computations using the tape, calculate the loss with the tape's context, compute gradients with respect to our variables, update the variable using gradient descent. We then run our training loop for 1000 epochs, training the loss for visualization. Looking at our results, we can see that the loss decreases steadily over time and our predictions closely match the true data. This low level implementation gives us control over the details while still leveraging TensorFlow's automatic differentiation. And then the next collab, in this collab, we'll see how to implement our neural network using TensorFlow's high level Keras API. Using the same quadratic data, we now define a model using Keras sequential, which allows us to stack layers in a layer fashion. Our architecture remains the same: an input layer, a hidden layer with 5 neurons each, and an output layer, all using the dense layer class. We compile the model with an Adam optimizer and a mean square error loss, then call model fit to train the data. Finally, we use model.predict to generate predictions in our data and plot the results. And the Keras API is incredibly concise while still producing great results. It handles all the details of the training loop, gradient computation, and parameter updates. And then moving on to the next third part of a neural network implementation, we are now exploring TensorFlow's functional API, which offers more flexibility than the sequential API. As with our previous examples, we'll use the same synthetic quadratic data to maintain consistency across our comparisons. The key difference in the functional API is how we construct our model. Instead of stacking layers sequentially, we explicitly define the connections between them. First, we define an input layer using Keras input, specifying the input shape. Then we chain our layers together by calling each layer as function, passing the previous layer's output as input. Our first hidden layer with 5 neurons takes the inputs. The second hidden layer takes the output from the first layer. The output layer produces our final prediction. And finally, we create the model by specifying the input and outputs using Keras.model. This approach gives us more flexibility to create complex architectures with multiple inputs and outputs or non-sequential connections. Although for this simple neural networks, it looks similar to our previous implementation. After defining the model, the compilation and training process remains the same as before. We use the Adam optimizer and MSE loss, then train for 1000 epochs. Looking at our results, the training loss decreases nicely over time and our predictions match the true data points well. The functional API is particularly useful when you need to build more complex networks with multiple inputs or outputs, or when you want to share layers between different parts of your model. And now we will move on to the TensorFlow sequential API with a slightly different approach. This is the most concise way to implement a neural network for straightforward architectures. We first create the same quadratic data as before. Using the TF Keras model sequential, we define our model as a simple stack of layers. First hidden layer with 5 neurons and ReLU activation. Second layer with 5 neurons and ReLU activation. Output layer with a single neuron and no activation. We compile the model using the string shorthand Adam for the optimizer and MSE for the loss function, which further simplifies our code. The sequential API is perfect for straightforward neural networks where layers connect in a simple chain. It's the go-to choice for many common applications due to its simplicity and readability. And now moving on to explore something different, which is visualizing four-dimensional data. This is a common challenge in machine learning where we often work with high-dimensional data sets. Here we are generating synthetic data with 4 dimensions, three spatial coordinates such as x, y, z, a fourth dimension w calculated using a non-linear equation. Since we can only directly visualize 3 dimensions in space, we use color as our 4 dimension, creating what's called a 3D scatter plot with color mapping. We generate 1000 data points with random XYZ values between -5 and 5, then calculate the corresponding W values using our equation. Using Matplotlib's 3D capabilities, we create a scatterplot where points are positioned in 3D space based on their XYZ coordinates. The color of each point represents its W value. Using the color map, a color bar on the side shows the scale of W values. This visualization helps us understand how the 4 dimension varies across the three dimension space. Notice the patterns and gradients in colors that reveal the underlying mathematical relationship. This type of visualization is extremely valuable when analyzing high dimensional data or when trying to understand the complex relationships learned by our neural networks in feature space.